Hello, everybody. Welcome back to Mathlete's Corner. We're 15 questions into the test, and this is where things start to get interesting. So, without further ado, let's get into problems 16 through 20 from the 2024 AMC8. So, starting it off with problem 16. Min enters the numbers 1 through 81 into the cells of a 9 by 9 grid in some order. She calculates the product of the numbers in each row and column. What is the least number of rows and columns that could have a product divisible by 3? So, when is the product of a numbers in a row or a column divisible by 3? Well, let's look at just a row. If the product of the numbers in a row is divisible by 3, that means that you need to have a multiple of 3 somewhere in the row. Otherwise, you wouldn't get a factor of 3 in the product. So, to start it off, the given 9 by 9 grid in the problem, well, that's really big. So, let's start off small and we can work our way up to 9 by 9. So, let's start with a 3 by 3 grid. Let's say we want to place the numbers from 1 to 9. Well, how many multiples of 3 do we have? We have 3 multiples of 3. 3, 6, and 9. So let's place the first multiple of 3 in the top left corner. And then the next multiple of 3, if we place it in any of these 4 squares that I'm putting a circle in, if we place it in those squares, then we'll lose 1 row and 1 column. But if instead we placed it in one of the squares with a rectangle here, then say, for example, it's this one, then we'll lose this row, but this column, we already lost it to the first multiple of 3. So it's optimal to place it in one of the squares with a triangle. All right, so let's place our second multiple of 3 here. By the same logic, let's place our third multiple of 3 there. So we've placed our 3 multiples of 3. How many rows and columns have a product divisible by 3? Well, that would be 4, because we have this row, this column, and this column. So it turns out 4 is optimal when you're using the numbers 1 to 9. You have 3 multiples of 3. You knock them off in the first row and you're done. But what if we still have a 3 by 3 grid? What if we have an extra multiple of 3? Well, you might be thinking that we can just place it here. Sure, we'll lose another row, and our new answer will become 5. But it turns out 5 is not optimal, because you may notice that if we put a multiple of 3 there, then we lose the first 2 rows and the first 2 columns, but nothing else. So the answer is actually still 4 in this case. So now we notice what's optimal. Now we notice the strategy for placing the multiples of 3. We want to place them in a rectangular grid. Just like earlier, we had a 1 by 3 rectangular grid. Now we have a 2 by 2 rectangular grid. So we want to place them into a clean rectangular grid as possible. So let's erase all of this real quick. And now we know how we can make progress in the problem that we're given in the 9 by 9 grid. So we have 27 multiples of 3. Now, say that our goal is to use only 10 rows and columns. Well, then the maximum number of cells that we could use is 5 times 5, which is 25, and we won't have space for all 27 of our multiples of 3. So that won't work. 10 won't work, and similarly 9 and 8. Similarly, 9 and 8 won't work. So let's see if 11 works. Well, if it's 11, we can just make a 5 by 6 grid, and we have 30 spots available. And now we can place all 27 of our multiples of 3. So our answer is 11, and we can move on. All right. A chess king is said to attack all squares one step away from it. Basically, any square right next to it in any direction, horizontally, vertically, or diagonally. For instance, a king on the center square of a 3x3 grid attacks all 8 other squares, as shown. Suppose a white king and a black king are placed on different squares of a 3x3 grid so that they do not attack each other. In how many ways can this be done? Alright, so quick summary of the problem. We're placing a white king and a black king on a 3x3 grid. We don't want them to be next to each other. Where can we start on this problem? Well, this problem demonstrates a strategy called complementary counting. Complementary counting. So the idea of complementary counting is to count what you do not want. So how many ways are there for the two kings to be next to each other? So let's start by counting that. Let's take a look at how we can construct a way for the two kings to be next to each other. So let's start by placing the black king. Right? So the black king, if we place the black king in a corner, then how many ways are there to place the white king? Well, if we want the white king to be next to the black king, then there's 3 ways. Like for this square with the 3 in it, you can use this, this, or this. So it's 3 for each of those. Now, what if we use one of these edge squares? Well, those squares have 5 adjacent to them. Now, what if we put the black king on the center square? Then there's 8 ways to place the white king, because wherever you place the white king, they're going to be they're going to be adjacent. So you can add those up for a total of 40. But 40 isn't our answer because we just counted what we don't want. So let's take a look at all the possible ways to place a black king and a white king. Well, there's 9 ways to place the black king and then 8 ways to place the white king because you can't place them in the same spot. So that's 72. So we counted the total, we counted what we don't want. So now all we have to do is just subtract. So we do 72 minus 40 and we get an answer of 32 and we can move on. All right. So a nice geometry question, problem 18. 3 concentric circles centered at O have a radii of 1, 2, and 3. Points B and C lie on the largest circle. The region between the 2 smaller circles is shaded, as in the portion of the region between the 2 larger circles bounded by central angle BOC as shown in the figure below. Suppose the shaded and unshaded regions are equal in area. What is the measure of BOC in degrees? So that's a lot of information. So let's start by finding areas, any areas. So let's zoom into the diagram a little. Here we go. So we're given the radii. So the inside circle has an area of pi. The larger circle has an area of 4 pi because it has a radius of 2. But let's look at the rings instead of the circles. So the medium ring has an area of 3 pi, and the largest ring has an area of 9 pi minus 4 pi, which is 5 pi. All right, so now what's the important piece of information that we're given? Well, the shaded and unshaded regions are equal in area. That's very important because we know that this part of the shaded region, let me actually highlight it with yellow. This part, this part of the shaded region has an area of 3 pi. We already found that. And since the total area of the whole circle is 9 pi, we know that the shaded area has to be 9 pi over 2. It has to be half of that. So the arc here, the area of this arc here has to be 9 pi over 2 minus 3 pi. And that would be 3 pi over 2. So now, since we want to find the measure of angle BOC, we want to find what fraction of the whole outer ring, which has an area of 5 pi, is just this portion, and which we found to be 3 pi over 2. So we can calculate that out. And that's just equal to 3 over 10. So angle BOC is 3/10 of the whole circle, which is 360 degrees. So what we're looking for is 3/10 times 360, and that is 108. And we can move on. Problem 19. Jordan owns 15 pairs of sneakers. 3/5 of the pairs are red and the rest are white. 2/3 of the pairs are high top and the rest are low top. The red high top sneakers make up a fraction of the collection. What is the least possible value of this fraction? So the idea here is that we want to minimize the number of red high top sneakers. So let's start by making a table. So we have red sneakers, we have white sneakers, and then we have the total. Then we have high top, low top, and the total. So we know that the total number of sneakers is 15 because that's given directly in the question. So we can go ahead and write that in the total. The next thing we were given is that 3/5 of the sneakers, of the pairs, are red and the rest are white. So that means that you have 9 red pairs, 6 white pairs. 2/3 of the pairs are high top and the rest are low top. So that means that there's 10 high top and 5 low top. Now remember, what we want to minimize is this portion here. We want to minimize the number in there. So if we want to minimize that, what do we have to do to the other 3 portions? Well, we have to maximize them. So let's quickly take a look at this portion here. Let me actually put that in a different color. This portion here. We want to maximize that. So let's say that all of the white sneakers are high top. All of the white sneakers are high top. So there's 6 white high top sneakers. So then how many red high top sneakers are there? Well, that's just 4. And that's the minimum it can be. The fewest number of red high top sneakers is just 4. Because if all the white sneakers are high top, then that's it. And just to make sure that this is a valid situation, we can say this is 5, this is 0, and we see that it works out. So 4 red high top sneakers out of a total of 15 sneakers gives us an answer of 4/15. And we can keep it moving. Now, another nice geometry question, problem 20. Any 3 vertices in the cube PQRSTUVW shown in the figure below can be connected to form a triangle. For example, vertices P, Q, and R can be connected to form triangle PQR. How many of these triangles are equilateral and contain P as a vertex? So let's see if we can identify any of the triangles that we're looking for, because the answer choices seem pretty small. So if we can just count it, then we'll be done. So once again, we'll zoom in and P. So starting at P, what are the lengths? So since we just want the triangles to be equilateral and we're not given any lengths, we can put lengths in ourselves. So let's assume that the cube is a unit cube, meaning it has side lengths of 1. So the distance from P to S, Q, and W is 1. So what's the distance from P to the other vertices? Well, P to V, R, and T, those are diagonals of a unit square. So those have a length of root 2. And that just leaves the distance from P to U, which is the diagonal of the whole cube, and that's square root of 3. So if P is if we have an equilateral triangle with a vertex of P, then the distance from P to the other two vertices has to be equal, because that's the definition of an equilateral triangle. So let's say we have, let's just show P there. Let's say that P has a distance of 1 from those two other vertices. Well, if we have something like PQ as a side of the equilateral triangle and PS as another side, then the third side, well, that'll be root 2, and the vertex angle will be 90 instead of 60. So that won't work. Similarly, if we have Q and W as the other two vertices, it won't work. W and S, same idea. So that means that from this case, we don't get any solutions. Now, from P to V, R, and T, well, you can choose any two of those vertices, and it will form an equilateral triangle, actually, because the distance from V to T, V to R, and R to T are all root 2. So whichever two you choose from V, R, and T, along with P, it forms an equilateral triangle. So from this case, actually I'll write it here. From this case, we get 3 solutions. Now let's take a look at this last case, P to U. So if it has a side length of root 3, then P needs to have a length of root 3 from 2 vertices. Here we only have 1 vertex, so that won't work. And so the 3 solutions we found are the only 3 solutions. And we're done. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next time here at Mathlete's Corner.